In this section, we're going to examine the method of finding volume of solids of revolution called the shell method. To find the volume of solids of revolution, remember those are ones that we get by spinning a region around an axis or revolving a region around an axis, you can use a variety of methods. We've already studied the disk and the washer method. The disk method, where we use the area of a circle and we integrate that. Remember, no matter what, volume is always the integral of the area of a cross section or a slice of our solid. So here we have the integral of pi r squared. Now I took the pi out like we normally do because it's just easier to write it that way. Washer is when we have a hole, and the integrand is the difference of the areas of two circles, pi r squared minus pi r squared. Now the cylindrical shell method is a little bit different. Let's take a look at this picture. Let's start by looking at this picture up here in the upper left-hand corner. We're revolving a region around a vertical axis. Instead of slicing into the region perpendicular, where we would just get a circle, we're slicing into it such that each slice is a cylindrical shell, meaning each slice is a cylinder, an infinitely thin cylinder. Imagine slicing that region such that you have stacked cylinders, like this picture over here in the upper right-hand corner. Now, if we're finding the volume, we want to keep taking those slices and slices and slices and stacking them together so that we eventually get the three-dimensional figure. But there is no top and there is no bottom, so the area that we're talking about is just the area of the sides of a cylinder. Well, what's the area of the sides of a three-dimensional solid called? The lateral area. The lateral area of a cylinder. Well, think about what that means. How can we make a cylinder with no top and bottom? Start with a rectangle. Roll it up like we're starting to do in these pictures, and there you have a cylinder with no top and no bottom. So imagine the length of the rectangle, that length right there, becomes the circumference of the circle. The circumference, 2 pi r, means the length of our rectangle, 2 pi r. Then the height of our cylinder is the height of the rectangle. So the area of that rectangle, which we know to be usually length times width, becomes 2 pi r times h. And that is the lateral area of a cylinder, 2 pi r h. Which takes us to our formula for finding the volume using cylindrical shells. Since volume is the integral of the area, in this case it's the integral of the lateral area of the cylinder, which means it's the integral of 2 pi r h, and because 2 pi is just a constant, we pull out the 2 pi and we're left with r and h. So two different scenarios to examine. If there is a vertical axis of rotation, like in this picture, the radius of the cylinder goes from the axis of rotation out to wherever the function hits. Well, because that is in the x direction, that's the x distance. The radius is the x distance. Now, because it goes right and left, that means we're going to compute that by right minus left, because it's a horizontal length. The height is the f of x distance. See, the height of our cylinder goes this way. The height goes up to the function f of x, y equals f of x. Because it's a vertical length, we measure it by saying top minus bottom. But when it's a vertical axis of rotation, we remember that we're using x's, x distance and f of x distance. Let's look at an example of using a vertical axis of rotation. Number 1, use the shell method, and I specify that because that doesn't always need to be used. When you learn this method, you'll learn that you have a choice and you pick the most efficient method to use. Use the shell method to find the volume of the solid described. Number 1, the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 2 revolved around the y-axis. So let's start by graphing this. Y equals x squared plus 1, parabola that starts up here at 1, and over 1 up 1, over 2 up 4. And we can do a little sketch of that parabola. We can sketch it to both sides. However, because of the nature of what I have to sketch later, I know I'm only going to be using this part of the parabola here. So let's continue. Y equals 0 looks like this. X equals 0 looks like that. And x equals 2 looks like that. So to touch all of those, I'm going to shade this region in here. And that is going to be revolved around the y-axis. So I'm going to trace over the y-axis and show that I'm revolving around that axis. Now, I'm making a cylindrical shell. So the shell, the height of the shell is parallel to the axis of rotation. The radius is perpendicular. The radius is always going to be perpendicular because it's going around like that. So the radius is from here out to here, and the height goes up and down. So there's a little version of my cylinder. So a vertical axis, r, is the x distance, and h is the f of x distance. If you draw it, it'll help you to see that better. So the x distance, x goes right and left. Here's my radius right here. I'm going to write r there, my radius. So I have to think right minus left. On the right is whatever x coordinate I'm at. On the left is 0. So for this one, x minus 0, or just x units away from that axis. The f of x distance, the height, is going up and down, so that's going to be top minus bottom. The top is the function, the parabola, x squared plus 1, and the bottom is y equals 0. To simplify that, we just write x squared plus 1. Now I remember that my volume is the integral of the lateral area, or just the area for short, which means it's the integral of 2 pi rh, or again, to make it a little simpler, bring out the 2 pi. The radius is x, and the height is x squared plus 1. Now, for my limits, if I'm using x's, my limits will be x as well. So these limits have to be x coordinates. So the shaded region is what I look at. From x being 0 to x being 2 is where this region goes, 0 to 2. And then I can evaluate the integral any way I want, by hand or with a calculator, depending on what I'm given. Now, for the purpose of our practice today, our goal is setting up the integral. We've set up the integral. We can carry on evaluating it later if we choose to. Look pretty good? Let's look at another. The region in the first quadrant, bounded by y equals x minus x cubed and y equals 0, revolved around the y-axis. Maybe pause the video and take a moment to try this one on your own. Come back and see how you did. Y equals x minus x cubed. Well, I'm going to factor that because I see that I have a GCF. Oops, excuse me. Let's fix that. I took out an x, 1 minus x squared. And we can find the zeros. X equals 0 and 1 and negative 1. So I've got 0. And because I'm only going out to 1, I'm going to stretch this. So I'm going to count this as 1. And it goes out to negative 1. Now, To do a rough sketch of this, it's going to look something like this. I only need the first quadrant, so I'm going to get rid of the part that is everywhere else. So it's just this. And then y equals 0, horizontal line like that. Now I'm going to shade that in and revolve around my axis, y-axis. Here's the y-axis, revolve around there. Now it's helpful to draw what the reflection looks like over on this other side, like that. We're using the shell method, so remember, revolve, that's maybe the top of the shell, here's the R, drop it to make my height. Because it's a vertical axis, R goes in the x direction, R is the x distance, and the height is the f of x distance. So the x distance goes right and left, so right minus left, and f of x goes up and down, so top minus bottom. Going right minus left is x minus 0, or x. Going top minus bottom is x minus x cubed, and then we plug it into our volume. Volume is 2 pi integral of the radius times the height dx, and then figure out where our x's go from and to. 0 in the shaded region to 1 in the shaded region. Yay! Let's see what this one looks like. The region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 2. So this looks like what we started with. Got part of the parabola and these vertical lines. Same thing we started with, but now we revolve about a different axis. The vertical line x equals -1. So we move it over here, going around that. If we draw what the reflection looks like to get a little idea of what it looks like, there's our solid. We revolve around this axis. So we can take our circle, top of the cylinder, here's our radius, and drop the height. There's our cylinder. Because it's a vertical axis, r is still the x distance, and h is the f of x distance. So still, for the x distance, that's right minus left, because it's going horizontally. Now this goes out to some x value, but look at what the left is. It's not at 0 anymore, it's at -1. So x minus -1. Or out x units, but we've added an extra unit to the radius. It was just this, and we've added one extra unit all along the way. So x plus 1. The height, still top minus bottom, which is the function x squared plus 1 minus 0. Now we get to go to our volume, 2 pi integral of r times h with respect to x. Now we do our limits. Now our limits, still x's, so we still want these to be the x values. What does x equal? And it's of the shaded region. The limits of the shaded region. So our shaded region, x limits go 0 to 2, still, because that's the only place we're putting shells in that region. Get it? Ah. Let's look at some more. Now we graphed this one earlier, but this time we're going around the line x equals 2. So we've got the origin over here, and I'm going to put the 1 out here. And so we've got our little x-intercepts, and our little region is right there. But this time we're going around x equals 2. So if this is 1, this is 2, here's the line about which we rotate or revolve our region. So the reflection is going to be approximately like this. Now notice how this time the reflection is on the right. Let's see how this changes what we do. We still have our circle where our radius starts at the axis, but it always goes to the original shaded region, not what we drew to help us imagine what the solid looks like. So this right here is our radius, and then we drop the height. Notice I'm always labeling it on the side where the original shaded region is. Okay, the original shaded region, that's where we label everything. Now, it's a vertical axis, so the radius is still the x distance, and the height is still the f of x distance. Because the x distance goes right and left, we still do right minus left. This time, however, on the right, that's the x coordinate 2. On the left is how far x units out we are from the origin. So this time, 2 minus x. The f of x distance is still going up and down, so that's f of x minus 0, f of x being x minus x cubed. Once we know our radius and height, the rest is a piece of cake. 2 pi integral radius times height dx, and now we find our x limits. Look at the shaded region, goes 0 to 1. So 0 to 1. I agree. Pretty cool. Let's look at a new region. The region bounded by y equals 4 minus 2x, x equals 0, y equals 0, and x equals 0. So this is a line starting at 1, 2, 3, 4, and has a slope of negative 2 over 1. Then we have x equals 0, y equals 0, and x equals 0, and there is our region. Where are we revolving it? The x-axis. We've got a horizontal axis now. Let's go up to our notes on a horizontal axis after we draw this reflection. So here, and a quick little sketch, and there we go. Let's look up at our picture. Horizontal axis of rotation looks like this. See how our shell is sideways of what we had before? So our radius goes from the axis of rotation in the y direction. There's our radius. The y distance, well, y goes up and down, so that is top minus bottom. The h, the height, is the f of y distance, and that goes horizontally, so that goes right minus left. Picture is very helpful when we do these problems. Let's draw our cylinder. So because this is the axis of rotation, our circle can be like this. The radius from the axis to the original curve, there's our r, and drop the height sideways. Because it's a horizontal axis, r is the y distance this time, and h is the f of y distance. That means everything is going to be in terms of y now. So the y distance goes up and down, so that is top minus bottom. The top is how far we are away in the y direction, so that's y, minus 0. It's only y units away, y units long. F of y means we need to solve this so it's in terms of y. So we solve this, we get x equals 2 minus 1/2 y, and this is the function in terms of y, f of y. So f of y, the height, is sideways, so that is going to be right minus left. The right is that line which we solved in terms of y, 2 minus 1/2 y, and on the left, x equals 0. Or just 2 minus 1/2 y, because we don't need to subtract 0. Then we put it into our volume. 2 pi integral of RH. R is y, and h is 2 minus 1/2 y with respect to y. And now we do our limits. Our limits are what y equals because we're using y. So looking in my shaded region, y goes from 0 up to 4. So our limits go 0 up to 4. Got it? Have you got time for one more? Let's try it. The region bounded by y equals x cubed, y equals 8, and x equals 0. Here we got a nice big graph. 2, 1, 2, 3, 4, 5, 6, 7, 8. And this, y equals 8 goes like this, x equals 0 goes like this, and we'll shade that nice little region right there. What are we revolving around? Let's take a look. Y equals -3. Going around there, let's draw our little reflection just to get an idea. So it looks something like this. Let's draw our shell. So going around this, there's the top of our cylinder, there's the radius, and there's the height. It's a horizontal axis, so the radius is the y distance, and the height is the f of y distance. Feel free to pause the video anytime and try to finish it on your own. Remember, when it's y, we want this in terms of y. So solving this equation is x equals y to the 1/3 or cubed root of y. So the radius goes top minus bottom because it's up and down. The top being how far we are away in the y direction, minus the bottom's not 0 anymore. We've added 3 units to it, so minus -3 or y plus 3. The f of y distance, the h, function minus 0. So the function y to the 1/3. Let's go ahead and plug that into our integral. Volume is 2 pi, integral of our radius, y plus 3, times our height, y to the 1/3, dy. Where are our limits? We want these to be what y equals in our shaded region, 0 to 8. And there we've got it. Thanks for sticking with it. See you in class.